we start with controllability in state space, that is part 2. Last time we have seen state controllability, that we have seen that the states which are at initial time that need to be transferred, and all state if it is transferred, then that is called state controllability. Then there is another word or another terminology that is called output controllability. Now, what is the meaning of this output controllability? In practice, we need to control the output rather than the state of the system. If you consider a classical system, we have output and input. Finally, output has to control. So, therefore, along with the state controllability, we have to control the output of the system. The complete state controllability is independent of output of the system. Therefore, there is need to check the output controllability separately. Now, what is the logic behind it? Last time I have given you one example about the students who are going from one place to another. Last time we have seen that an industrial trip is going from some place just like IIT Roorkee and they are going to some Delhi, and there are 10 students are going, assuming that 10 students, and now we considering that these 10 students are the states of the system, and all these states has been started at some time and they have reached to Delhi, let us say x1, x2, x10. So, these states have been reached, and we have seen that if any of the states has been missed, that is any of the student has been missed from this place, let us say this is x9, this has been missed, then we have seen that that particular system is not controllable. No, but assume that the all states are here, they have been reached here, all students at IIT Roorkee, they started from here, they have reached to Delhi, then why there is need for output controllability? It is because the students have come here to Delhi for some industrial trip. Assume that all students have reached, but let us say the company has denied to enter because the output in this system is to reach to the industry, but to certain reason it is not possible. That means that even though your state has been reached here, but you are not getting the output. Therefore, there is a need to have output controllability also, that output also to be controlled. So, but how to test it in a mathematical aspects? Last time we have seen, if you want to check the controllability of the system, we have written the controllability matrix as Q equal to B, AB, just like that, A raised to n minus 1b, and we are checking the determinant or rank of this matrix. If rank is full, the system is controllable. And in this case, in case of controllability, we have seen there is no C matrix has been involved. But this is the output controllability. It means that something, that means C matrix, which is important in output, that must be involved because that is concerned with the output. Therefore, the test which is required to check the controllability is represented as shown here. Let us say x dot and y. This is our system, state space system, and we are talking about the output controllability. So, what is said? The above system is output controllable if it is possible to construct an unconstrained control signal u of t that will transfer from given initial output y of t0 to any final output y of tf in a finite time interval. Here we are talking about the state at initial time, then reach to final time, but the output controllability is concerned with the output at initial time and what is the final time. As we have seen that Here we are output, we are concerned with to reach the industry, or some practical problem occurred, output is not possible. So even the state has been reached, but we are not getting the output. So that means that output is not controllable. Therefore, output controllability is also very important tool whenever we are studying the control in all respect, in terms of stability, modeling, in terms of controller design. Now, how to check the output controllability? Now, this is a plant. The above system is output controllable if and only if the composite matrix Q. Now, this is Q, this is output controllable matrix, and we have to write in this form CB, CAB, CA n minus 1 B, this. So, we have to determine the rank of this matrix. The rank of this matrix must be M. So, M is, you see, order of C is M cross M. So, this particular M. So, order of this is must be M. Similarly, if D is not equal to 0, that means when D is existing, that means our output controllable matrix we have to write in terms of CB, CAB, CA square B, CA n minus 1 B, and this D part is will come, whereas in D 0 this D is not present, and for all this case your rank must be M. Now, we will try to solve an example and we will see that that particular system is output controllable or not. Okay. The state controllability is also, we can write in this way, the state controllability is different from output controllability. For controlling the output of the system, the complete state controllability is neither necessary nor sufficient. That means both output controllability or state controllability are independent, but as I told, for complete analysis of the system we need to check both state controllability as well as the output controllability, because our practical sense we have an output, therefore output is very important. Okay. Now, we start with an example. An example is of second order system, and for the system we will check the controllability, output controllability of the system. And for this example we have already seen how to check the state controllability. Now, just see it. Say x1 dot, x2 dot, say 1 1 minus 2 minus 3, say x1 x2 say 0 1. Now, this is a state space system, but in this case this is a state equations, and if you want to check the controllability of the system, this is A and this is B. We can easily check the controllability by taking QC B A into B. But now here we required output controllability, and when, as I told you, output controllability means that output C matrix plays an important role. Therefore, for this problem we should also know the output equation. Therefore, the output for this, say 1 0 x1 x2. So, this now it is A, B and C has been defined. Now, just see the formula for output controllability. The output controllability is CB, CAB, CA raised to n minus 1 B. Now, in this particular problem you have n is 2, therefore, A order of A will be 1, therefore, we have to take CB and CAB. Now, Q output controllable this is given as CB and CAB. Now we will determine CB as well as CAB. Now, just see CB What is the C matrix? C matrix is 1 0. And what is B matrix? The B matrix is 0 1. Now after solving 1 into 0, 0, 0 into 1, 0, so now CB is 0. Now coming to CAB, CAB, so C is 1 0 and A is 1 1 minus 2 minus 3 and B is 0 1. Now we have to solve this equation. Now here 1 multiplied by 0, 0, 1 multiplied by 1 will get 1. So we can write down this as 1, and here minus 2 multiplied by 0, 0, minus 3 multiplied by 1 will get minus 3. And after solving this, 1 multiplied by 1 and 0 multiplied by minus 3, so we will get 1, and therefore this Q matrix, that is OC, that is output controller matrix, that is O is output, C is controllable, we can write down as 0 1, and from this we will find that the rank of this rank, this is equals to m, that is equals to 1. Because of 0 it becomes 1. So rank is 1, and what is m here? M is also 1, that is a row, we can say 1. So therefore it is satisfied our conditions, that is this condition, as we discussed, these conditions of rank is satisfied in this particular example. Therefore this system is output controllable. Therefore if you are given any system and we have to design a controller, the controller can be designed only when system should have these particular properties. If system does not have a output controllability as well as the state controllability, then it is difficult to design a controller. But sometime in a practical systems, and system involves so many state, and we have to design a controller. So in from practical point of view, we should have some more flexibility in the designing of the controller. Therefore in a control there is one concept is present, that concept is called stabilizability. This is also a very important concept from control point of view, and this concept is also related to our controllability. Now how it is related? See here, stabilizability is a weaker notion of controllability. That is, controllability is there, this is a weaker part, that is partially controllable, we can say, that is stability means we can say partially controllable system, that is not a fully but partially controllable system. See here, partially controllable system, it is defined as the uncontrollable modes are stable and unstable modes are controllable, that is called stabilizability. Now how we think about this stabilizability concept? Again we come to the example which we had taken earlier, that is here there are 10 states, or we can say there are 10 students here, they are going to Delhi from Roorkee. Now here this is IIT Roorkee and it is Delhi, and the students are going for some industrial trip at Delhi, and therefore there are states again x1, x2, x10, and we have seen that if all states which are at IIT Roorkee, all students which are there at IIT Roorkee, when they reach to Delhi, we have observed, let us say all 10 states or 10 students are available, or we have observed, or we can say they are present there, we are saying that your system is state controllable, but any of the state is missing, we are saying that it is not a controllable system. But as student has reached to Delhi, and as a teacher I have to take to the say for industry, but I observe that one is missing, the state is missing. Then can I, as I told earlier, that when any of the student has been missed in that industrial tour, it is difficult for a teacher to carry out the student for industry. That means he has to come back and he has to see where is this. So if the similar situation happened, if any of one of the student has been missed in that industrial trip, so what is the best option? I will see where is that student. Suppose I got information that student which has been reached to Delhi for industrial trip, but at the same time he has left to some his relatives. If that information I got and I talked to him that okay, he is there, but he told me that because of some health problem he is not coming to this one, that means I got idea that the student even though reached Delhi, but it is not observing, therefore, but he is somehow stable. Then what I can do, out of this 10 I will take 9 students to the industry, knowing that one is not there, he is in relative's house, his health is not good. So in such case we can say that system is in stabilizable mode, or this is called a weaker notion of controllability, or we can say partially controllable system. Now we see this part through an example. See here, this is x1 dot, x2 dot. Now here 2, 0, 0, minus 2, say x1, x2, 1, 0 into u. Now this is our system, x1 dot ax plus bu, and now we are talking about the stabilizability, and as I discussed that stabilizability is nothing but a weaker notion of the controllability. As looking after this system 2 0 0 minus 2, and here we got 1 0, and this part is coming in a Gilbert test, and in the Gilbert test if you have seen that if the given system, if it is in diagonal form or particular A matrix in the diagonal form, we have to see the B matrix, and if any of the element in this B matrix, this is B matrix, this is A, if any of the element in this B matrix is 0, then system is not controllable. That part we have seen, and this is Gilbert test. Just looking after the example, we observe that this system is not controllable. But now I have to work on the system. So just looking after the system, we observe that, see here, this is 2. This 2 is a unstable system, because if you take the stability of the system, you will find that the eigenvalues at lambda 1 equals to 2 and lambda 2 equals to say minus 2. So here the system is unstable system. Out of this we find that the 2 indicate the unstable part of the system, but that unstable part is there. If you see the 1, that is a controllable, that is unstable part is there, but it is controllable. But if you see the this is a minus 2, which is the stable part, this is a stable part, but 0 is the uncontrollable part. That is, if the system having this type of property, that is this unstable part is controllable and stable mode is uncontrollable. If this is the situation, then this is called stabilizability of the system. As we discussed, it defined as uncontrollable modes are stable and unstable modes are controllable. So here we have seen the same part. This is the unstable mode, it is controllable, where stable mode is uncontrollable. So this is called stabilizability of the system. Now coming to the another issue, that is called pole 0 cancellation. Actually pole 0 cancellation, this is the part which is concerned with the say transfer function, because transfer function involves poles and 0, but as for state space there is no such issues. We are x dot equals to ax plus bu, we got ABCD matrix. So, the concept of pole 0 is also related to this controllability and observability issues. This is because even though system it is in a transfer function, we are converted into state space. Suppose if you have a system which is given in a transfer function domain, and if there is a pole 0 cancellations. So, just cancelling a pole 0 here, can we say that system is not controllable? So, here the system is not controllable. So, but if we are saying system is not controllable, what is the reason behind it? Can we prove it? So, here our philosophy is associated with the pole 0 cancellation. So, it is said that necessary and sufficient condition for complete state controllability is that no cancellation occur in the transfer function. That is, if you take any transfer function, if there is any cancellation of poles and 0, system cannot be controllable according to the theory. That is, if you take say s plus 1, s plus 1 and s plus 2, if this is a plant, actually mathematically we are cancelling this and we can say s plus 2. So, mathematically s plus 1, s plus 1 we cancel, we got s plus 2, everything is stable, that means that that is system is stable, controllable, everything we can observe, that means mathematically this is true, but from control point of view this is not true. It again we can say that this is although the mathematics is important in the control system, but from practical point of view or from control point of view, every concept of mathematics cannot be applicable directly for the control system analysis. Here this is the same issue, s plus 1, s plus 1, we cancel 1 plus s plus 2, and the more severe condition will come when we can say s minus 1, here s minus 1, s plus 2. So, this is the system we cancelled, here 1 upon s plus 2. So, this system is stable, but this cancellations cause problem to the controllability of the system, even the stability of the system. In earlier part we have already seen say s minus 1, say s plus 2, this is say g of s. Now, if you solve it, we will get s minus 1 s square plus s minus 2. Now, from mathematical point of view, if you talk about mathematical point of view, this s minus 1 will cancel, we will get s plus 2, and we can say that system is stable. And same thing, if you are taking care of state space analysis, if you develop the model of this plant in a state space, this x dot equal to ax means here 0, 1, 2, minus 1, x plus 0, 1 into u, and y equals to minus 1, 1x. So, the same plant, if you have not done any pole 0 cancellations, we get s minus 1, s square plus s minus 2, now here 0, 1, 1 minus 2, 2 minus 1, and if you check the stability of this model A, so we will find that there is also one eigenvalue on the right hand side, let us say at 1, and here is minus 2, and now this is unstable. So, you find that if you do the pole 0 cancellation, the original system we found stable, but actually it becomes unstable. So, there is the instability issue, but similarly there is also issue with the controllability of the system. If there is a pole 0 cancellation, we say that the system is not controllable. Now, we see another example. Suppose if you write phi s by u of s equal to s plus 2.5 s plus 2.5 s minus 1. Now, this is a plant, and what we are saying that this is s plus 2.5, s plus 2.5, s minus 1. So, this s plus 2.5 and this we can cancel easily, and we will get s 1 upon s minus 1. So, now according to the concept we are, as I discussed, the system is not controllable, but can it really true? To check it, what we do? We can use our conventional approach. For the conventional approach, what we can do here, we solve this equation s plus 2.5 divided by s square plus 1.5 s minus 2.5. So, after solving this, we got this. Here we have cancelled 1 by s minus 1, and mathematically we have done like this. And now we are talking about the controllability concept without any pole 0 cancellation. Whatever system we have keep as it is. Now, what we can do? Now we determine a state space model of the system. The state space model of the system is, say, x dot equal to ax plus bu. Now, the A matrix in this case is 0 1 2.5 minus 1.5, and if you see the B matrix is 0 1, and the C matrix 2.5 and 1. So, this is a controllable canonical form, or we call as a companion form of matrix. Now, we try to check the controllability of this system. Now, we have to check the controllability of the system. Now, for checking the controllability, what we will do? We will write this as B AB matrix, and if you do it, so what we will get? Your B is 0 1, and this AB matrix, if you multiply, you will get here 1 minus 1.5, and if you calculate the determinant of this, if you take the determinant of this, what will take? We will get minus 1 is not equals to 0. So, minus 1 is not equal to 0, that means that your system is not is controllable. So, as we discussed earlier that our this system is uncontrollable because there is a pole 0 cancellations. So, the thing is that this we have done in case of the controllable canonical form or companion form, and we say that in this particular form, this AB and AB, it does not depend upon this mathematical matrix S plus 2.5. So, whatever may be any elements in the numerator is not affected by B and AB, particularly if you write the given system in this controllable canonical form. Therefore, if you want to check the controllability when there is a pole 0 cancellation, I think we have to involve the elements of C matrix, that is elements of C matrix, because C actually doing the pole 0 cancellations. Therefore, we have to do or make arrangements such that in the elements of B there must be the elements of C. So, this is possible if you convert this system into the observable form, that is controllable observable canonical form. So, observable canonical form means this A changes to A transpose, and this C transpose equals to B. That means here I am writing down here this side, this A matrix. Now, here actual A matrix become A transpose, this A transpose is 0, 2.5, 1 minus 1.5, and here this B matrix. So, that means here this A transpose is nothing but A matrix observable form OBS, and again here B observable equal to C transpose equal to 2.5, 1, and now here if you solve it, B observable, A observable to B observable matrix. So, you find that this B observable. So, B observable matrix is 2.5, 1, and now A observable is like this, and if you multiply by B observable here, we will find that it also become this multiplication of this A observable this and B observable this. If you multiply it, we will also get 2.5 into 1, and if you take the determinant of this equals to 2.5 minus 2.5 equal to 0. Now, you will find that this system is not controllable, that is the pole cancellation we are directly reflected through the mathematical approaches of checking the controllability of the system. Therefore, whenever any system is given to you for designing of the controller, then in that case if there is a pole zero cancellations, we can't design a controller. That means, if you are given system in a transfer function model and if the pole zero cancellations, there is no need to design a controller. That means system is controllable, that means that particular state cannot be controllable, that means that there is no need to go for the controller design. Now, these are some references. Now, this is the part concerned with the controllability of the system, but in a control application along with controllability, we need to know the observability of the system. And what is the observability, how it is useful in a state space analysis, particularly in control design, that we will see later on. Thank you.